Hey, what's up, YouTube? I think that we're live now, and let's also go live on Twitch as well. What's up, everybody? Welcome back to my practice stream. If it's your first time, my name is John, and today we will be practicing some more linear algebra. Today is July 1st. The last time that we were in Chapter 10 was June 8th, so almost a month away. And now we are solving large linear systems. So this is applying linear algebra to actual engineering problems where matrices are not 2 by 2 and 3 by 3 matrices, but enormous matrices, like hundreds by hundreds or thousands by thousands, millions by millions, literally billions by billions. Like ChatGPT and other AI-based models are essentially working with humongous, billion by billion dimensional matrices. So we're working through this book, Fraleigh and Beauregard. I haven't written out the table of contents, so why don't we do that now? Chapter 10, Solving Large Linear Systems. I hope y'all are having a good day. Solving large linear systems. Cool. I'm having a bit of an existential crisis because I am hoping to hear back about some of my recent interviews, but I haven't heard back yet. Both of them, I don't know. I'm still waiting to hear on two different ones that I think went well. But, maybe I missed it. Maybe they don't like the idea that I have a YouTube channel or something. I think that that's very possible. Maybe that's not a good thing to have a YouTube channel and be a high school math teacher. I don't know, dude. Maybe it's not. Maybe I should just delete this whole thing, because that is the priority. The priority is getting into a classroom and helping little kids learn mathematics. Considerations of time. Is section 1. Then we have section 2 on the LU factorization. And then we have 10.3 on pivoting, scaling, and ill-conditioned matrices. Pivoting, scaling, ill-conditioned matrices. Awesome. Hey, what's up, Arad? How's it going? Oh, bro. I am having a bit of an existential crisis, my friend. Luna! My cat wants to say hi. Let's let the kitty cat in. I forgot to open up the Twitch dashboard, so I don't know. We might already have a chat. Nope, no chats yet. Okay, as expected. Hi, baby. Yeah. I feel like I'm mostly concerned just about the gap in... the freaking crazy gap in my resume. Which makes sense to me. Like, I can describe it if somebody asks directly about it, because it was an entrepreneurial attempt, to try to build my own businesses. I had a couple of things like that were tech products, specifically tech products for musicians. But I'm afraid that somebody's I'm just not going to get the interview in the first place. Like, I'm just not going to get the question in the first place about why there's such a large gap in my resume. All right, so let's just jump into it. I don't know if I want to solve a problem from 10.1. Considerations of time. This is kind of analysis of algorithms. I've done like a whole book on this stuff. I mean, I think I can try. Section, let's do it. 10.1, considerations of time. Let A be an n by n matrix. Doesn't say real valued or complex valued. And let's see, find the number of flops required for efficient computation of a square. Unfortunately, nowadays, I don't even know if CVs make it to humans. Yeah, see, I mean, literally, I actually am concerned about that. I'm like, I wonder if my CV just isn't even making it to a freaking human because I don't have a master's degree and I don't have formal classroom teaching experience. And I think that what I am missing there, I've gained in real world industry experience, like working at large tech companies, like working at Apple, Lyft, Google. But that might just not be part of the prompt, to an AI that's filtering resumes. Like somebody might be like, must have either a master's degree or, classroom experience. But I've already gotten the attention and met like I've run interviews at this point. Like I have shown my resume to humans, and I'm just like, why have I not heard back yet? Like I feel like my background is impressive in that I would pick somebody with that background even if they didn't have classroom experience, but maybe not. Maybe I just don't know what I don't know. Like, I know classroom management would be a difficult thing to learn, but I think I could learn it. I really do think I can learn it. I just know, like, pure math experience is not directly exactly what like running a high school math class is like. That's a little more babysitting skills, which I have some. I've worked with kids for years. Okay, well anyways. To compute an entry in a squared, we compute for row vectors, for row vector AI and column vector AJ in matrix A. For this dot product AI.aj. This is going to be a I1 times a 1j plus a. Oh, well, now we should use the same. Oh, wait, no. This is fine. A I to a 2j plus dot 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 a I n a n j. So, which has n multiplications and n minus 1 additions. Right? Yeah, because for every term there's a plus. You need to add 2 of these terms. So there's n minus 1 additions. So AIJ requires n times n minus 1 flops. There are n squared entries, so naive question mark implementation requires, yeah, this seems really terrible. N to the 4th minus n cubed flops. If you multiply n times n minus 1 by n squared, we get n to the 4th minus n cubed. Pretty sure that there's a more efficient way to find the square of a matrix. It feels like there should be. Definitely feels like there should be something more efficient. What's up, Prani Dawan? How's it going? Hello. Is it your first time here in the chat? Nice to meet you, dude. Nice to meet you. And Dan the King on Twitch. What's up? Thanks for the follow. I see we got a follow on Twitch. What's up, bro? So I'm trying to find the number of flops for computation of a squared. Pretty sure a single entry in the naive implementation by the frickin' definition, there are n multiplications and n minus 1 additions. Oh, wait. We don't do n multiplications times n minus 1 additions. This would be n mults plus n minus 1. So 2n minus 1 flops for AIJ. Right here there was a mistake. Yeah, we need to add those together. Yep. So now, somehow I thought that it was n cubed. So now this is looking a little bit better. 2n cubed minus n squared flops. Yeah. I think that that's it. I wonder if there's a speed up that we can make. I'm not studying maths. You're just interested. Let's go, dude. That's the idea, bro. Yeah, you just came in interested. Dude, that's the idea here. Like, I feel that this could be a really cool study with me kind of stream, for people who aren't even studying math. You're studying cost management accounting. Let's go. That's awesome. Cool, Sudeep. Yeah, there's so many linear algebra books and courses and things like that out there, software. So that's pretty awesome. Cool. All right. I think that this is correct. I'm actually, I think that this is a good use of ChatGPT, to be honest with you all. Yeah, I've never learned this in detail, but supposedly for small sizes of matrices, there's various algebraic tricks to speed it up. Yeah, I think that there's all kinds of speed ups. That this is just a naive implementation. This is just a direct implementation, and there's a lot of work that people do to try to speed up these matrix multiplications, because this is literally ChatGPT. ChatGPT is like lots of large matrix, multiplications. Yeah, Dan the King is talking about the JE. I've heard it's very hard, man. I've heard it's very, very hard. Someday I'd like to learn it and practice some JE math. Yeah, I feel pretty confident about this answer. I don't even need to check. I'm feeling super confident about this one. All right, let's keep going. Let's just keep going. I'm going to cross out this problem. Okay, jcpractices. Yeah, dude. I mean, I think that'd be fun to work JE at some point. NEET is also has tough maths. I'm from India, by the way. Nice, dude. Nice. Awesome. Here, I'm gonna type this for you. Okay. So that was that problem. Now the LU factorization, we're going to go on to the next section. Section 10.2. The LU factorization. What's the next problem? We've got find the solution to this system given L/U is written as 1, 0, 0, 1, 0, negative 1, 2, positive 1, negative 1, negative 2, 1, 3, 2, 1, negative 1, 3, and B is this. So I think of this as like yesterday we solved this. We solved a system and then we wrote down the steps that we took, and now we've forgotten A. We don't even know what the original matrix A was. But we found the steps. We wrote down the steps that we took. And the steps are this lower triangular matrix. So 1, 2, 3, 4. It's a lower triangular matrix. 0, negative 1, 2, negative 2, 1, negative 1. So there's L. And then U is this upper triangular matrix. 1, 0, 0, 1, 0, negative 1, 2, 1, 0, 0, 1, 3, 0, 0, 0, 3. So we find C so the original solution is 4, 7, negative 8, 14. And then based on L, I see that we added the first row to the third. We did not add or subtract the first row from the second, but we added the first row to the third, and we subtracted 2 times the first row from the fourth. So 14 minus 8 is 6. And this is because L1 or L3 1 is negative 1. Therefore, row 3 prime is row 3 plus row 1. So I added row 1 to row 3 as one, just writing out that example. And then this next one was L4 1 is positive 2. Was the step that I took. Now, looking in the second column, we add 2 times the second row to the third. Add 2 times the second row to the third. So we keep those entries the same. add 2 times the second row to the third would be 14 minus 4 is 10. And we subtract the second row from the fourth. So we subtract the second row from the fourth, and we get this. Now, the final steps, we add. So L4, 3. L4, 3 is -1, right? Yeah, -1. So therefore, 4, 7, 10, we add the third row to the fourth. So 10 plus -1 is 9. And now this is C in our matrix equation UX equals C. We could do back substitution, or we could solve using U. Yeah, I just prefer to do back substitution with the matrix. Which, slightly different than the book does it. The book always does back substitution with the raw equations, but I just think it's much cleaner now that we've practiced this a million times to solve matrix systems this way. We may as well continue doing it this way. So the fourth row divides by 3 to get x4 equals 3. We could subtract the fourth row from the third, and then we get -1. We can subtract the new fourth row from the previous second row. So I subtract, I've got 7 minus 3 is 4. And I can subtract the new fourth row from the previous first row. So 4 minus 3 is 1. And now we're very close to done. Hey, Luna, did she just destroy my book? She may have just destroyed my book. Oh my gosh, it's still hanging on by a thread, dude. This book is hanging on by a thread. This book is actually literally hanging on by a thread here. Thank you, Luna. I feel maybe when the book actually falls apart, then we move on to a new book. We're so close. Let me read. Oh, you did a numerical analysis. Oh, and you're doing, you solved LU by hand, like how I'm doing, right? It's crazy. Yeah, I had never really learned it before. As awesome as it is knowing all the abstract theory, it's worthless if you can't shut up and just compute it. Yeah, what is your motivation? I want to get a job, dude. I want to get private students. So if anybody wants a private tutor, I am available. jcpractices@gmail.com. And I want to prove to people that I can be a really awesome high school math teacher. Yeah, because it's kind of an uphill battle, it feels like right now. Even though I'm totally freaking qualified and, I can do it. But Okay. Let's flip the sign of the previous equation just so that we can see it more easily. Now I add 2 times row 3 to row 2. 0, 1, 0, 0. So add 2 times row 3 plus old row 2. So -2 plus -4 is -6. And voila, now we have our solution vector. One, -6, -1, 3. And we've solved it. That book was getting too much attention. If I was a cat, I'd be jealous too. Yeah, it definitely does have a lot of attention. Even class 10 math was tough. I heard for Central Board of Education, gave JE level questions for class 10. Why don't you take degree to teach? I already have a math degree from a long time ago. And I worked in software for 10 years. I worked at Apple, Lyft, and Google. I'll do a math degree, or I'll do a degree if I need to, but I feel that I'm totally ready today, you know? Like, I'd rather just get started now because I feel I'm fully qualified and ready to just get started immediately, you know? Yo, what's up, Geometry? How's it going, bro? How are you? Oh, I forgot to turn... sorry. I don't intend to keep Hawaii on for the whole stream. Dang it. Dang it. Here. What's the deal here? Aha. This is weird. Okay. Notification enabled. Let's go. Let's go. I'm happy to hear that. Okay, wait. Here, I'm gonna fix a thing before I forget. I have to fix a thing really quick. My button is broken. Now my button is working again. Cool. Okay, so I think I solved this problem correctly. We could take a look in the back of the book, potentially. Is this an odd problem? I don't know if this book will ever actually fall apart. It's actually hanging on by a thread, but I think that thread is going to actually last forever. So, unless I, like, intentionally destroy it. Yeah, this is an odd problem. So number 7 in section 10.2. This is the next to last section in this book. So we've been ripping all the way through the entire book. What did I do wrong? Okay, one... Shoot. Where did I make a mistake? Okay. I got something slightly different. Let's see. 4, 7, 10, 9. Let's double check our... Oh, you know what? Okay, if I subtract row 4 from row 3, this should have been positive 1. Yeah, this one should have been a positive 1. Oops. And then if I add 2 times that... Well, what am I doing? Okay, 7 minus 3 is positive. Okay, it's positive 4, and then I multiply by a negative. Okay, yeah, that's fine. And then add 2 times that to the second row. This should be negative 2. Oops. Calculations are hard. Negative 2. 1, negative 2, negative 1, positive 3. Is that the answer in the back of the book? Calculations are hard. (10.2) number 7. 1, negative 2, positive 1. Oh, yeah, positive 1. I copied it wrong in this. Oh, I fixed it in one spot but not the other. There we go. Okay, I see why. Yep. Now it's fixed. Haha. Okay. We got it. We got the important part. We definitely got the super important part, and then chat distracted me. You all distracted me, I'll say. Okay. So that was section 10.2, and I can cross out this problem. I did it. I hope I can finish quickly so that I can practice some inner product problems. I think that I need a bit more practice on the inner product. Because I've been struggling with a problem in the representation theory book, which, by the way, tomorrow we're going to be back to representation theory. I'm excited. And we're going to do 4 streams in a row, representation theory, starting tomorrow. Heck yeah. Pivoting, scaling, and ill-conditioned matrices. (10.3) Find the solution without pivoting by a 5-figure computer. So this is floating point arithmetic with 5 significant digits. So I'll say now, the goal, we've been doing high school calculus, college linear algebra, grad school or research level or something, representation theory. Right? This might change because right now I am applying to a middle school role. This might change, and we might add in basic mathematics by Lang. I think this would be fun. This would be middle school / high school. Then, college level, I might just bump up calculus up to college and keep grad school as rep theory. This might happen, like a new stream structure. Hey, how's it going? Yeah, if I want to prioritize inner products, I think I want to get in a flow where I'm just adding in review as I need to. So if I finish a practice session, then review some other topics. I'm also studying on my own privately. I'm starting to get in the habit of also studying off camera, which I think is, it's pretty good for me. 200x2. Okay, so we want to see what happens if we use 5 significant digits in our floating point arithmetic. Is the solution accurate? If not, if so, modify the system a bit to obtain one for which a 5-figure computer does not find a reasonable solution without. If so, modify so that the solution is unreasonable. Okay. And in rep theory, the first chapter is a review of linear algebra, and it's really proof theoretic abstract linear algebra. So we're going to continue practicing and learning linear algebra in chapter 1 of the representation theory streams. Like, we might be done with working on linear algebra as its own book, but I want to make sure I keep coming back and repeating and refreshing and practicing this stuff. So I don't know. Okay, with 5 sig figs, what happens? Do I need to scale every row first? I forget the process in this. Like, am I supposed to blindly follow the algorithm? I believe I am supposed to. I can't just notice that I can add the first row to the second, I think. Or maybe I do. Do I scale every row to have a leading pivot of 1 or not? Yeah. Okay, so we preserve this first row. And then in the second row, I I think I'm allowed to just add the two. If I add If I add 200 to 1 million with 5 significant digits, I think we still have 5 sig figs here. And so we don't lose accuracy. Because you're allowed to have 5 significant digits, if I understand correctly, multiplied by 10 to a digit. I think that this is another bit of information. So the fact that in this case it would be 10,002 times 100, I believe, is allowed. Now we divide the second row by that. When we do that division, we get 0.999. Let's restyle this as some side work. This is 0.1234. It's approximately equal to 0.12349s. I think that this is an exact equation right now. And then this is the same as 99990 with 5 significant digits. So we don't lose any info. Okay, now we are going to evaluate in floating point arithmetic, what is this minus a million times 0.9999? So this is a million. 1, 2, 3, 4, 5, 6. So we move the decimal point 6 places to the right. 1, 2, 3, 4, 5, 6. And this difference is just 100, right? Yeah. With 5 sig figs, we'd have this. And then we get something that's almost exactly the mathematical this is almost the exact solution. Therefore, our solution it's very close to the exact solution. To modify this system, I think we just need to add a couple more zeros to the coefficients to make unreasonable notice that the point in which we did not lose any accuracy was in this step, right? The 1,200,000. So I think that if we if we modified the coefficients to be 10 millions, like multiplying every... I think if we multiply both rows by 10, we would immediately... we would break this system of equations. Let's move this and do this in another area. Here. So the solution should be exactly the same, but I think that we'll see that we hit floating point errors if we multiply both equations by 10. So we add a 0 to all of the coefficients and remove these commas. And then I'm pretty sure that this would break the system of equations. We'd get floating point errors that give us like a completely wrong answer. Hey, what's up? Oh, anything. Yeah, dude. Anything. Sorry, I missed your question. Yeah, where should you start? If you're interested in engineering, I would start from the very first linear algebra sessions. I really think linear algebra is incredibly useful for engineering. So I would watch my chapter 1 videos, dude. Start from those. Yeah. Okay, I gotta be right back, y'all. Be right back. going? Oops, I accidentally hit the wrong button. What's up, everybody? I'm back. Let's get back to practicing math. So, in exercise 3, I think that we get a reasonably accurate solution. Reasonably accurate, and then modifying. I don't know, they gave an interesting other example. I see. Yeah, if you... 1, 2, 3... Yeah, another way that would also break this system I think that if we multiplied everything except for the 100, or like the 100 places, like this one wouldn't be able to be solved. Because then when you add the second row to the first, we lose the information of that 200. Because then adding those two together would give us 10,200,000, but with 5 significant figures, this is rounded down to 10 million. So this can't be solved. Alternatively, instead of making it more complicated or larger numbers, I could maybe divide the second row by 10 instead. This one also can't be solved. As this requires 6 significant figures, or the part leading up to the 0, 5 sig figs would be 1, 2, 3, 4, 5, 0, 0. One, two, three, four, 5. So to 5 significant figures, we just lose the that 20. Hey, what's up, Doge? Gosh dang, what are these questions? How's it going, man? I am doing some floating point math right now about matrices and finding a solution to this system of equations that a computer can solve if a computer has to round to 5 significant figures. So, do you know anything about floating point arithmetic? Like a computer can't represent an infinite decimal. It just can't. It doesn't have infinite bits. It's not able to represent an infinite number. So every computer has to work with some amount of rounding. This is called floating point arithmetic. And so if we have a 5-digit figure, like 1, 2, 3, 4, 5, this number is 5 significant figures. It's 5 digits. If I added the number 6 to it, so this one requires 5 digits, and then you can always multiply by a power of 10. This one only requires 1 digit, so we can also represent it with a computer, and, well, we don't have to multiply by any power of 10, right? So a computer can store both of these and it can represent both of them. But when it adds those numbers together, 1, 2, 3, 4, 5, 6, it can't represent all of this because it needs to only use 5 figures. So it needs to round either up or down. In this case, it looks like it would round up and say that these two are quote-unquote equal. Like in floating point arithmetic, these two are equal. Why don't I solve some physics? Because I don't want to. I want to solve math. Are you more interested in physics? Yeah, I'm doing calculus, linear algebra, and representation theory. I'm doing a lot of linear algebra because I think linear algebra is really nice, really beautiful. Yeah, I do pure math. I'm a pure mathematician. Yeah. Nice. Okay, so I think we're done for today. We just solved the very last section of this book. Yeah. Heck yeah. We just worked one problem from the very last section. Ooh, what's representation theory? Oh, that's a great question. So, it's the study, this is the beginning of it. The study of symmetry using linear algebra. If you don't know, linear algebra is kind of like matrices. So we represent symmetry of an object, symmetries, we literally represent those symmetries with matrices. Let me give you an example. If I have a square, I could label the vertices 1, 2, 3, 4, right? If it's a perfect square, I can rotate that square, and then I have the same exact square, but the vertices have changed, right? Like I can rotate a square. I can rotate it a total of 3 times, and then on the 4th rotation we go back to the original square. So if I rotate again, we get 1, 2, 3, 4 like that. And if we rotate again, 1, 2, 3, 4, then if I rotate one more time, we come back to the original square, right? Yeah, you use matrices to describe symmetries of objects. Exactly. 1, 2, 3, 4. There's another symmetry that we call mirroring, or S for some reason. I'm not sure if it's maybe a German word or something. But what this one does is it flips along one of any different axis. But usually I use the vertical, like a vertical reflection, right? So we could, so this is another type of symmetry. Now, what happens if I take any of these? First off, I'm going to name the first one E, like the original, we call it like the identity. It's kind of like multiplying something by 1, like don't do any rotations. This would be doing 1 rotation. This one is doing 2 rotations. This one is doing 3 rotations of the square. Now, what happens if I apply a mirror? So applying, like, this is really function composition. So I flip 2, 1, 3, 4. If I do function composition here, and this would be SR, I flip 1, 4, 2, 3. SR squared, so rotating twice and then flipping, 4, 3, 1, 2. And then the final one, if I rotate 3 times and then flip, I get 3, 2, 4, 1. If I look at all of these are all different. Every single one of these is a different orientation of the square. So this one is just, the only thing that we do is just a mirror. So these are all 8, I think we call them rigid symmetries. These are the exact 8 rigid symmetries of the square. Where is this useful? It's used actually in physics, now that you mentioned it. Like crystals, like crystalline structures exhibit symmetries. And theoretical physics, like everything about string theory and all sorts of crazy theoretical physics stuff, uses symmetry all the time. Like, this is the beginning of something called group theory, and you could look this up, that group theory is used in physics a lot. Yeah, symmetry is used a lot. but I'm interested in it just because it's like a really pretty, nice field of math that is just, it's just pretty. It's just really pretty. I don't know how else to say it. But notice that if I just stay with rotations and I keep rotating, I get 4 symmetries. And if I keep just flipping, I get two different, I stay within that little subgroup. Like if a group is a collection of symmetries, then these are 2 subgroups, and you just stay within those 2 subgroups. Now, take a look at this matrix. Have you seen matrices before? If A is this, then A squared is... Have you seen matrices? Ooh, this is related to Noether's theorem and analytical mechanics. Nice. I don't even know anything about that. That's cool. Okay, so if you know about matrices, then we take the dot product of the first row and the first column. So this entry, okay, you know matrices, nice. So then this top left is -1. The top right would be 0. The bottom left would stay 0. And then the bottom right is -I times -I is I squared, which is -1. So A cubed would be, if you see it as A squared times A, then this would be -I, 0, 0, +I. A to the 4th then would be, well, you could do A squared times A squared, and we get 1, 0, 0, 1. A to the 5th, well, that's A to the 4th times A. A to the 4th is the identity matrix, which does nothing. It like keeps the, it preserves the identity of whatever it multiplies with. So now, again, we have this exact same little loop, this exact same freaking structure. So it's we could call it a 4 cycle, which is exactly the same as this 4 cycle. And if I let this matrix, I think it's I and -I. Is this correct? So B squared is B times itself. -I squared is 1. Top right, 0. Bottom left, 0. Bottom right, -I squared is +1. then we have a 2 cycle. Just like this 2 cycle, right? So we have 2 different types of cycles. Now, in D8, we have a relation that says that SR to the N is... Oh, wait, no. RS is the same as SR cubed. Let's see, what do I mean by this? If I have a square, which I'm just going to start writing as 1, 2, 3, 4 like this, then applying S is flipping along the vertical axis. And then if I rotate after this, then we would have 3, 2, 1, 4. So this is RS. So first flipping and then rotating. But what if I have the square and I rotate 3 times? I wrote that earlier. But if you rotate 3 times, we'd have this. It's the same as doing a negative rotation, actually. And then if I flip this thing, then I get 3, 2, 4, 1, and boom. These two are the same. RS is the same as SR cubed. Oh, the stream is buffering? Bro, is it bad? I'm sorry. Is it still pretty bad? Yeah, this is a graduate level topic. I mean, you can study this in as a math major. It's kind of a math major, upper division math major topic. Now, my next question is, so a rotation I wrote as matrix A, and a reflection I wrote as matrix B. Does this equal BA cubed? Does this match the same structure that we have over there? AB is I negative I. B was 0. I think positive I and negative I. Yeah. This is 0. This is negative 1. This is negative 1. And this is 0. So this is AB. Ooh, BA cubed. Is that? Oh, yeah, okay. So we get that, and then BA cubed is BA is this matrix, 0i, negative I, 0. And we found earlier that a cubed is negative I, 0, 0i. So, this is kind of cool. So those matrices, in some sense, they actually represent the same symmetries as the symmetries of the square of D8, which is super cool. Super freaking cool. Oh, now it's good. Okay, cool. Hey, Sumit, I'm doing good. Can you solve some JE problems? No. Not unless you pay me. If you pay me, I will. But I'm studying math for fun that I want to study. Okay, so I wanted to hit some inner product problems. And I did a bunch yesterday on paper. So let's do a couple here. Vectors in Euclidean algebra. Matrices in their algebra. Norm and dot product. I think I did all of these. Prove that the angle between two unit vectors u1 and u2 in Rn is arc cosine u1 dot u2. Okay, this isn't too bad. This is fairly straightforward, I think. The norm and the dot product. Oops. Prove, it does say prove. This is fairly easy. But it is a proof nonetheless. There's no numbers. We're not doing a computation. Amusing Yourself to Death and Mood Machine. Yeah, these are excellent books back there. How, like, you can actually read the titles of those books? Dude, how do you know? How can you read those titles? I didn't think that you'd be able to read those. Amusing Yourself to Death is a phenomenal book. Great book, dude. Great book. All of those books are. So, we have... Let's remember that for any two vectors, A dot B is length of A times length of B times the cosine of the angle between them. So, because u1 dot u2 equals length of u1, length of u2, cosine of their angle. Because you are unit vectors, their lengths are 1. The norm of a unit vector is 1. That's kind of the definition of a unit vector. So u1 dot u2 equals cosine theta. Taking our cosine of both sides, then theta equals arc cosine of u1 dot u2. And we're done. Cool. That's not the hardest problem ever, but I hope you all followed that. Let's keep going. That was one problem from there. Now let's see. There's a section on inner product spaces. Linear transformations. Let's get to the inner product spaces section. Ooh. Okay. Inner product spaces. So, determine whether this thing is an inner product. Where let C negative 1 to 1 be the vector space, the vector space of all continuous functions So, recall the definition of an inner product. We need, and right now this is from a vector space into the real numbers, which is a little weird because later on we learn, well, Why do I think about jazz while studying? I'm not thinking about jazz. Are you? Are you talking about the background music that is playing? All the background music is classical guitar, and that's me. That's my classical guitar music. If you enjoy it, I would love to see you sometime in the guitar stream. So these are the definition, or this forms the definition of a real valued inner product. Some type of music. What? Have I completed any game? Not in a long time. How do you get yourself to study when you're tired? Drink coffee, I guess. That's one way. I probably will not play GTA 6. No, I don't really play video games anymore. I used to play a lot of video games. I completed lots of video games when I was a kid, you know? Nowadays, math is my video game. So we check each axiom. P1 is satisfied. I think all of them are. Maybe not the last one. I have to think about that last one. The inner product of f of x, gx because these are real valued functions, the multiplication is commutative. And now this is that works. Then P2 let F, G, and H be in C -1, 1. Then the inner product of F with G plus H is defined as the integral from -1 to 1 f of x times, I should write technically G plus H of x dx, and the addition of those two functions is g of x plus h of x. And the integral has this linearity property. I don't know if I'm supposed to have brackets around all this. And now this is the inner product of f with g plus the inner product of f with h. So the second axiom is satisfied. The third one is pretty clear as well, I think. Let f and g be continuous functions on this interval and r be a real number, then rfg maybe from here we could go to this point, or we could go from that equality to this next one. So we get all of those properties that we needed. Oh, hey, what's up? Yeah, we're convoluting. What's up, dude? Yeah, my parents both love math. Yeah. It's not a convolution? I thought it was. It's going. Yeah. Okay, now the last one is the only one that I was unclear about. P4. Well, yeah, it has to be. Yeah, no, this is true. Yeah, certainly. Right? Because f is real valued. Because because f is in the real numbers, then the function value is in the real numbers, so the square of every point is non-negative, right? And this is the integral of the zero function on that interval is 0. Now, to prove that it equals 0 if and only if f is exactly 0, I think here we need to use continuity. Do we need continuity for the integral to exist in the first place? I think so. Suppose that equals 0. I mean, if f is 0, then certainly the this convolution-like thing. If f is 0, then this is fairly clear to me. If f equals 0, then the integral from -1 to 1 f of x squared dx equals 0. Do I need to, like, partition the interval into, like, I don't know how formal we're supposed to get here. Like, can I just say this implies f is 0 because f must equal 0 at every point otherwise there exists a neighborhood such that for all x minus some there would exist a neighborhood around some non-zero point don't know, clean up the writing in this a little bit, but if there's some non-zero point, then let's say that it equals some epsilon greater than 0. Then we can split this integral to, we like partition the interval into 3 portions. I should really say y by continuity of f. Like, since f is continuous, then pretty much by the definition of f, of continuity, for every epsilon, we can find a delta such that blah, blah, blah. Well, we could say that f of x naught is some constant greater than 0. Then we can find an epsilon greater than 0, say epsilon equals c divided by 2, and then this is like essentially this integral would be non-zero, and then the other two would be equal to 0. Oops. So if in other words, I've just shown essentially, I think, the contrapositive. That if there exists some non-zero point, then on the unit interval, or from -1 to +1, then ff is not 0. Yeah. Could f be negative here? F could be negative, but but the inner product of f with itself takes square values, right? So it's not Axler. No, this is Fraleigh. Yeah, I mean, I think I pretty much have. I've definitely convinced myself, for sure, that yes. That this defines an inner product, a real valued inner product. Yeah, the square. Oh, when I said f of x naught. Oh, my bad. Yeah, there was definitely a place where I wrote that incorrectly. Okay. Yes. F of x naught is some constant. Yes, my bad. That constant can be either positive or negative, then f of x naught squared is strictly greater than 0. Yeah, my bad. So f of x squared is strictly greater than 0 for every point in that interval, so then the integral will be strictly positive. Why did I say that this equals k? Or equals 1. So I think I've shown the contrapositive. SVGs can contain links? Are you serious? I had no idea that that's the case. That's disgusting. Are you serious? An SVG can have a link in it? That's horrible. I do not want my images to have links. I definitely do not want images to have links. Okay, so I've done a couple of inner product problems. I'm just doing some extra problems, some extra work today, because I got a little confused by the first problem in tomorrow's representation theory stream. We're going to be getting back to some representation theory soon. I'm excited. Where is the more general definition of a Euclidean inner product? Here we go. Now, in section 9.2, this is the form of the inner product that I should be memorizing. Complex valued inner products. Ooh. Okay, wait. This is CN. I want an even more general inner product definition, I think. Huh. Is it in an exercise? I bet it's an exercise, isn't it? Or maybe it's just not covered. Yeah, I think it's just not covered in this book. Oh well. Okay. Definition of the Euclidean inner product. So let's say that U and V are vectors, are complex valued vectors. Then the inner product of U and V is U1 conjugate V1 plus U2 conjugate V2 plus ... So you need to conjugate one of the two terms. And then from this, we can get this theorem, which says that we have the inner product of U with itself is greater than or equal to 0, and U equals 0 if and only if U is equal to 0. Part 2. UV is equal to VU conjugate. So I need to learn that. I need to memorize that. But we do have this additive property. U plus V W equals UW plus VW. It's interesting that the book writes it slightly different. Oh well. And then this book also shows WU plus V I don't know if I'm ever going to be able to keep these straight in my head. Like where we keep the conjugations and where we don't. I'll definitely be able to memorize this one. I remembered this when I was writing down the real valued inner product. I was like, yo, I feel a little unhappy writing this first property because I do remember that it's reflexive in the real numbers, but you have to conjugate in the complex valued numbers. And I guess I'll be able to remember additivity. But then, how in the world am I ever going to remember that you can factor out of the first component with a conjugated factor, but you can factor from the second component without conjugating? I don't know how I'll ever remember part 5. Hey, what's up, Sana? How are you? The conjugate of a real number is itself. So I remember that. That's easy. Yeah, I can remember that, but I don't know how I'll keep this factoring straight. Factoring from the first component conjugates the factor, but factoring from the second component does not conjugate. I mean, I suppose I can prove it with that this one by a previous property yeah, I mean, I guess I see that it is true. So maybe if I just memorize the first part that that factoring from the first component conjugates the factor, then I can remember this. I can prove the second. Okay. In some parts of physics / applied math, it's more conventional to have the conjugation in the first component, while pure mathematicians often prefer the other way. Yeah, I felt like this is a thing where you could define it in either component. Like, I felt like this depends on whether you conjugate the first factor or the second factor in this definition, right? It's all convention. Okay. So that's the definition in Fraleigh of the Euclidean inner product, and I don't think I've done any problems yet. But I could do this one. I need to get some proof-based ones if I'm going to actually be able to solve the next exercise, I think. But let's do a problem anyways. 9.2, skipping ahead and looking at problem 14. Find each of these. Inner product of 2 plus I feel 2 plus I, 2I with 1 plus I, 2 minus I. 1 plus I, 2 minus I. Well, this is going to be 2 plus I conjugate times 1. Plus 2 conjugate times 1 plus I plus I conjugate times 2 minus I. 2 minus I plus 2 minus I. So that conjugate of 2 is 2. Oh, wait. I did an extra conjugation, didn't I? Yeah. What am I doing? Slow down. 2 plus 2I. And now conjugate of I is negative I. So we have negative 2I. Negative I times negative I is I squared is negative 1. Add all the real components. 2, 4, 3. Add all the imaginary components. Negative 1, positive 1, negative 1. So we've got 3 minus I. Part B. Is this really the most valuable thing to do with my time right now? 1 minus I. 1 plus I. 1 plus I, 1 minus I. So I'm going to start jumping ahead. So this is going to be 1 plus 2I plus I squared. 1 minus 2I plus I squared. Add all the real components and they add to 0. Add the imaginary components and they sum to 0 as well. I noticed that these are conjugates of one another, right? The terms. So is that always true? I don't know. Part C. Ugh. One plus I. 1 minus I. 1. Inner product of that with I, 1 plus I, I, 1 minus I. So 1 minus I, I'm spotting in a couple of places. And 1 plus I see in a couple of places. So this is, I can factor out 1 plus I times 1 minus I plus 1 plus I. This is 2 plus 2I. Because the second term adds to 2, and then I factored 2 in with 1 plus I. Part D. This is the last one. 2 minus I, 3 plus I, 1 plus I, inner product with 1 plus I, 2 minus I, and 1 plus I. Is that right? Physicists use inner products so much. If they develop the convention, it's probably because it's convenient. Yeah, see, I don't know. Like, I haven't seen the usage of this in physics very much. Like, I did take a quantum course, so I probably did use this, but I don't remember it. I don't really remember it very well. Okay, so that's inner products according to Fraleigh. Let's very rapidly write down inner product according to Steinberg. Or probably according to Axler, I would also get, I think, the same as what Steinberg has. Because I saw an inner product from a vector space, from an arbitrary vector space in this book. Okay, so we have this linearity property in the first component. We have this conjugate reflexivity, and we have this positive definite thing. Is that what this is called? So this is now a definition of the inner product for an arbitrary vector space, not Fraleigh first defined the inner product from R squared into R, then the inner product from C squared into C. But now Steinberg is doing V squared into C. And I gotta get going. This stream has gone on long enough. But just so you know, this is the exercise I've been chewing on and which I want to tackle tomorrow. Steinberg exercise 2.3 says let V be an inner product space and let W be a subspace of V. Let V be in vector space V and define V hat as in the proof of proposition something or other. So V hat is the orthogonal projection of V given an orthonormal basis EI. Then it says prove that if W is in your subspace with W not equal to V hat, then the norm of V minus V hat is strictly less than the norm of V minus W. Deduce that V hat is independent of the choice of orthonormal basis. For W, it is called the orthogonal projection of V onto W. So this is the exercise that I've been chewing on and trying to figure out how to prove. So, thank you everybody. I appreciate your time, your attention. Thank you. Thanks for watching. Please do like and subscribe. And if anybody is curious, we do have a Discord. that I'm trying to build up with math enthusiasts. So if anybody wants to join the Discord, would be great to have you there. There's also a link, I believe, in the description of this video, or link in bio as well. Have a good one. You too, dude. You too. Thanks for stopping by. Bye, everyone. Bye. Take care. Bye. Oh, and yeah, starting tomorrow, we're going to be back to representation theory. Excited for this new round, a new bout with rep theory. All right, take care. Bye.